All right. Okay. Can you guys hear me?
Yes.
Yes.
We don't have any issues with Zoom today. So hope the exam went well on the CBTF system worked at least reasonably well. It's not perfect, but I didn't see too many people having problems with scanning the exams in time. And so, do you have any questions about the exam or comments? Was it the right length, and did I give you enough hints to get you started? I hope.
Well, I mean, reasonable.
Questions were based on things that you saw in the homework, so or things we discussed in the review session. So I was hoping that you shouldn't have had any difficulty if you were following the material in class. So okay, so today's topic is going to be inequality constraints, and actually let's look at the previous lecture, not 13. 13 was a actually 13 was 13 was actually about Lagrange multipliers. Actually, we did examples mostly in 13, I guess. But so we looked at Lagrange multipliers with equality constraints, and then this was the key result with about necessary conditions. So you first check if X star is regular, and then a necessary condition for it to be a local minimum is this equation, the Lagrange multiplier equation. Okay, and then we also looked at second order conditions. Maybe get to the final result. And we'll talk about how it's related to what we're going to talk about today. Okay, so this is the result. So the necessary condition in terms of the Lagrangian, so the gradient of the Lagrangian has to be 0, and of course X star and lambda have to satisfy these two equations, and then the second order necessary condition is given by this expression here. So it says that the Hessian of L is not quite positive semi-definite, but if it's positive, it has the properties of a positive semi-definite matrix for all z belonging to V of X star, the ones for which z is orthogonal to all the gradients of the constraints functions hi. Okay, and then, but more importantly, you can get sufficient conditions for a minimum in terms of this Hessian, and for that you need strict inequality here. Okay, and we saw this even before with unconstrained optimization. Okay, to get sufficient conditions, you need strict inequality, a strict or positive definiteness in that case. Okay, so today we'll talk about what happens when we add inequality constraints in addition to equality constraints. Okay, so we're going to look at this problem here, where we're trying to minimize this function. You have the same old equality constraints that we saw before, hi of x equal to 0. But in addition, we have gj of x less than or equal to 0 for j equal to 1 to r. Okay, so we'll call this the inequality constraint problem, or ICP. Okay, and as usual, we're going to assume that f, hi, gj are continuously differentiable, and when we need second order sufficiency conditions, we'll also assume twice differentiability. Okay, now we can write the constraints, these constraints, all these m constraints, compactly as one vector dimension, a vector valued function x equal to 0, and the inequality constraint as some vector valued function less than or equal to 0, with the understanding that when you have a vector valued function and we say that it's less than or equal to 0, then each component of that vector valued function has to be less than or equal to 0. Okay. All right. So that's so a lot of times in books you'll see the constraints written in this compact manner. All right. So one important consideration when we talk about inequality constraints is the difference between active and inactive inequality constraints. So constraint, say gj of x less than or equal to 0 is said to be active okay, at some point x if gj of x is equal to 0. So the constraint is basically the boundary of the constraint. Okay? That's when it's said to be active. And it's said to be inactive if the inequality at that point is strict. Okay. Now we'll denote all the indices j, so all those constraints for which gj of x equal to 0 as a set of active inequality constraints. And we'll denote that by script a of x. So for each x, okay, we'll have a set of active inequality constraints, a of x. Right? Is that good? Now, why active versus inactive? It turns out that it's only the active constraints that play a role in the constraint optimization problem in terms of how they affect the necessary conditions. Okay, so we will establish that more formally soon, but I'll give you some intuition for why that's true. So the claim that I'm making right now, this is just a more of a more in terms of more intuition rather than proof. So we're going to claim that x star is a local minimum for if x star is a local minimum for this this original problem, the ICP problem, then it's also a local minimum for an equality constraint problem where you throw away all the inactive inequality constraints and only keep the active ones. So we'll minimize f over the equality constraints hi of x equal to 0 and all the active inequality constraints for which gj of x is equal to 0. So basically we can discard inequality constraints in the search for local minimum. In other words, the inactive inequality constraints don't really play a role in the necessary conditions. Okay, so let's see. First, let me give an intuition for why this is true, and then we'll go over the proof, which is a little bit detailed. So there's a lot of steps to the proof, but we'll give some intuition for why this might be the case first. So what happens with these inequality constraints that are not active? Okay. So let's actually just look at the case where you're trying to minimize f with just one inequality constraint. Okay, g of x less than 0. G is just a real valued function. Okay. So suppose x star is a local minimum for this problem. Okay. And it turned out that the g of x star is was strictly less than 0. Okay, so in homework 3, you showed that if G is continuous, the set of X such that G of X is less than 0 is, what kind of set is that?
Open.
Open. So, okay, so actually let's look at that set here. Okay, so this whole thing with the boundary, it may not be convex necessarily, unless when will the set be convex? For example, if G is convex, right? Okay, but in general, it may not be a convex set. So there's the set, but the boundary of this set corresponds to the equality constraint G of X equal to 0. But if I'm inside, right? So if I'm inside that, so the interior of this set is the set of X's for which this is a strict inequality. So if I'm inside, since this is an open set, if X star is sitting here, all directions are feasible from that point, right? All directions are feasible. So if all directions are feasible, then what's the necessary condition for X star to be a local minimum? Yeah.
Gradient equals 0.
Very good. So just the gradient equals 0. So the constraints don't matter for interior points, right? We saw this more generally in lecture 10 when we looked at a minimization over closed convex sets. Right? So the constraint does not affect the necessary condition. Okay. So we could basically, in that case, ignore the constraint in determining, to getting an equation for X star. It's just the gradient of F that matters. And this argument really carries over easily to multiple Gj of X star less than 0. So it's basically only the active inequality constraints at X star that matter. Okay, so that's just a high level intuition, right? For why only the active constraints might matter. Okay. Now let's go back and look at this equality constraint problem where we got, call that ECP. ECP is ICP with keeping only the active inequality constraints for which Gj of X is equal to 0. So we call this ECP. So we look at this ECP. This is a problem we solved already, right? In lectures 11, 12, 13 here. We talked about that, right? And we know how to do this. So if X is regular for this problem, and regular for this problem means that the gradients of the HIs along with the gradients of these GJs, the ones that belong to the active constraints, they all have to be linearly independent. So if that's the case, then we can write down a Lagrange multiplier equation for this problem. Okay, so let's do that. So assuming that X star is regular for the equality constraint problem, that means gradient, if I look at the gradient of HI of X star, So, or maybe I should list them all. H1 of X star, gradient of HM of X star. And then along with all the other gradients of the GJs, but the GJs, I'll only look at the ones that are in the active set. If these are linearly independent, then we know from the Lagrange multiplier theorem that there exist Lagrange multipliers. We'll call them lambda for the HI constraints and mu j for the mu for the GJ constraints. So there exist these Lagrange multipliers such that if I look at the linear combination of the gradient of fx star plus I equal to 1 to m lambda I hi of x star, and then I'll look at the equality constraints corresponding to the active inequality constraints, which are j belonging to active set, mu j gradient of gj of x star equal to zeros. This really follows from the solution that we gave in lectures 11 and 12.
Did you forget putting gradient to h?
Oh, gradient, yes, sorry. Yeah, forgot to put a gradient there. Yeah, very good. Okay, so if we could stop here and just, if you agree with the intuition for this problem, but of course, you know, we also need to prove it formally. But there's another little thing that we can end up proving for inequality constraints that we don't have, for active inequality constraints that we don't have for equality constraints. Okay, for equality constraints, the lambdas, and you saw these examples in the homework and in class, the examples we discussed in class, that the lambdas could be positive or negative, right? Depends on X star. For some X stars, lambdas could be positive, or some of the lambdas could be positive, some of the lambdas could be negative for equality constraint. But it turns out that for the active inequality constraints, the mu j's will always be non-negative. Okay, so we'll establish this, and there's some you can, there are some, if you look at the book, there are some pictures in there which I actually didn't, I forgot to get them, get the PDF versions of those images to show you. Or maybe next class I'll show you. But there's some pictures that kind of illustrate, give you some intuition for why the mu j's have to be non-negative. But what we're going to do here is actually prove that they're going to be non-negative. Okay, prove formally that they're going to be non-negative. And along the way, we're going to establish this result that we can discard the inactive inequality constraints when we consider necessary conditions. Okay, so we'll do both. We'll show that ICP is really equivalent to this ECP. Okay, and that we can and that we have that the Lagrange multipliers associated with those active inequality constraints have to be non-negative. Okay. So is it clear where we're going with this? Okay.
Yes.
All right. So this we're going to capture all of that in the following result, which are called the Karush-Kuhn-Tucker necessary conditions, or KKT. So this result is probably one of the most important results that you learn in this course. and you you know, if you have anything to do with optimization after you're done with this course, okay, you're going to have lots of occasion to use this results, the KKT theorem. Okay. And by the way, who are these people? So Kuhn and Tucker were, one of them was a Canadian mathematician, and the other was an economist. I think Kuhn was an economist, and Tucker was a mathematician. And they wrote this paper in which they proved this result for inequality constraints. And then it was only a lot later, actually. So it was called the Kuhn-Tucker theorem for a long time. It was much later, I'm not sure, even maybe it was even in the 2000s that, or in the 90s or something, that people someone actually found a master's thesis by somebody called William Karush from 1938, in which he had the same result. Okay, he didn't publish in a paper, he just had it in his thesis. So there are some beautiful master's theses out there. In fact, actually, Claude Shannon, the father of information theory, also did some very important work in his master's thesis, which is on Boolean algebra. Right? So this is one of those examples of a master's thesis that contains a very important result, which was not published anywhere else except in the thesis. So, so now it's called the Karush-Kuhn-Tucker necessary condition, or Karush-Kuhn-Tucker theorem. All right. So, so if you look at the ICP problem, we can define a Lagrangian function that involves all the HIs, the linear combination f of x plus all the linear combination of the HIs and all the linear combinations of the GJs. It'll turn out that it's only the active ones that matter in this linear combination, but we'll get to that in the statement of the theorem. So what this theorem states is that if x star is a local minimum for the inequality constraint problem, and that x star is regular, and it's regular for this equality constraint problem. It's regular for this problem. So it's in the sense that these guys are linearly independent. Only the active ones here and the H's have to be linearly independent. Okay. By the way, in order for these gradients to be linearly independent, it's obvious that m plus the number of active constraints has to be less than n. So we saw that when we just had equality constraints, it required m to be less than or equal to n. Here we need m plus the active inequality constraints to be less than or equal to n in order for them to be, in order to get a regular x star. Okay, to keep that in mind. All right, so suppose x star is regular for the equality constraint problem, then there are unique Lagrange multipliers, lambda 1 through lambda m and mu 1 through mu r, such that the gradient, okay, of the Lagrangian with respect to x, right? Again, so you take the gradient of this guy and the gradient of this guy and add them up. So that's equal to 0. And mu j is greater than or equal to 0 for all j, and mu j is equal to 0 for the inactive constraints, so they don't really matter. So all that's captured in this result. Okay. Now, in addition, if these are twice continuously differentiable, then we also have the second order necessary condition. And the second order necessary condition, again, it's like a positive semi-definiteness condition, but only on the set of first order feasible directions. You remember our V of x star, but V of x star is now defined with not just the gradient of the HIs, but also the gradients of the GJs that are in the active set. Okay, so we require all these to be 0. Okay, so only those y's for which all these inner products are 0, only for those y's you need to check the PST condition. Okay, so this is the key result, and we're going to go over the proof of this result. Okay, so it's going to take us a little while, so we'll spend most of this lecture, I mean all of this lecture, remaining of this lecture, proving this. But again, it's a complicated proof, so I don't expect you to, just necessarily just get it in one try. But it's important for you to actually see the proof at least once in your lives. So if you have anything to do with optimization, so just just ask questions. Stop me if you need to, but then you may need to go back and read the proof on your own again to make sure it sticks with you. Okay. All right. Okay. So what do? So you take your inequality constraint problem, right? And you convert it into so you take your inequality constraint problem and convert it into an equality constraint problem, but not by discarding all the inactive constraints, but actually keeping them and actually showing that they can be discarded. This is the difference. We're not going to discard it this time. So we're not going to convert ICP to ECP like we did here. We're not going to say, well, this problem ICP is equivalent to this problem directly. We're going to prove that. But then how do we replace these inequality constraints with equality constraints then, without just throwing them away? Okay, so what we can do is the following. So if an inequality constraint is inactive, that means there's some gap between Gj of x and 0. So I'm going to introduce an auxiliary variable to fill that gap and make it equal to 0. Okay, I can always do that. Okay, but what does that buy me? So we'll see. Okay, so I'm going to add to this function Gj of x. I'm going to add a variable Zj. Okay, Zj squared actually, because I know that the gap to 0 is something positive, right? Because Gj is less than 0. So I'm going to add a positive number in order to make that constraint equal to 0. Okay, but now think of the Zj that I added as an auxiliary variable. I'm introducing new variables into the optimization problem that were not there before. So now I have to deal with them too. But it turns out that there's an easy way to deal with them. That's what makes this proof possible. Okay, I'll do that for all, both active and inactive constraints. For the active ones, Zj will be 0 automatically. Okay, and for the inactive ones, Zj will be positive. Zj squared will be positive. All right, so our auxiliary variables, I'll call them Z in a vector Z, the Z1, Z2, up to ZR. Okay, so now this problem, which I'll call P3, is an equality constraint problem, but it involves both X and now these auxiliary variables Z. So over 2 sets of variables, eh? Okay, that's fine. It's still an equality constraint problem now. So you're minimizing over f of x over these equality constraints, but this is an optimization problem over x and z. With z only appearing in the constraint. Okay, so what I could do is I could think of this as f of x and z, okay? But where basically that function is really not a function of z. It's constant as z varies. It's only a function of x. Okay. Similarly, h of xi and x can be thought of as a function of both variables, in which the second variable really doesn't matter. Variation in the second variable doesn't matter. The z only appears in this constraint here, right? Okay. But it's still a valid optimization problem with equality constraints, but optimization problem over these two variables, x and z. Now, if x star is the local minimum for the inequality constraint problem, then it's clear that x star and a corresponding z star is a local minimum for this problem P3 but you have to make sure that zj star is actually minus gj x star to the half. If I do that, then with that zj thrown in there, right? Then all these equality constraints will be met. Okay, so I could then focus on P3 and look for conditions for which this combination x star z star is a local minimum for P3, and that'll give me a necessary condition for the ICP problem as well. Is the logic clear? Seems like we are cheating, but we're really not, because we're going to actually make sure we're careful with that second variable, z. Okay. Okay, so let's look at the first order necessary condition for the P3 problem. Again, we have to assume that x star, the combination x star z star is regular for P3, but it'll turn out that that regularity condition is the same as is actually this regularity condition that is for the ECP problem, that one that we stated in the previous, this one, that only these guys have to be linearly independent. And we'll see why. But okay, so let's assume that x star is regular for P3. X star z star, sorry, is regular for P3. In that case, by our first order necessary condition for the LMT, Lagrange multiplier theorem that we proved in lecture 12, we know that the gradient of L with respect to both variables, x and z, right, has to equal 0. So basically, maybe I should add that. So this should be gradient with respect to x and z. Or maybe that's what I meant to write here. Okay. Has to equal 0. Okay, let me just remind you again in case you forgot. This is the first order necessary condition from lecture 12, right? Gradient with respect to x has to equal 0. but let's look at what the gradient with respect to both these variables is. We can actually stack the components of the gradient, right? So we'll take the gradient with respect to x and set it equal to 0, and then gradient the separate gradient with respect to the z variables and set that equal to 0, because the gradient is a concatenation of both. So let's do the gradient with respect to x. If you look at the gradient with respect to x, then let's see if the gradient with respect to x of this function involves only these guys. It doesn't involve this last term. Okay, so let's write that down. So that's gradient with respect to x gives me gradient with respect to x of f plus summation I equal to 1 to m lambda I gradient with respect to h, and the gradient of the mu j, the gj, sorry, gj. Maybe that should have been a j there. Okay, all these are gradient with respect to x. At x star. Now let's do the gradient with respect to z. Then these guys will not play any role. They'll go to 0, and it's only the last term. Okay, so let's write that down. So I'll get summation j equal to 1 to r mu j gradient with respect to z of zj squared. At z star. Everyone see that? So when I take the gradient with respect to both variables, I can first take the gradient with respect to x. I get an equation corresponding to that. And then I'll get a gradient with respect to z. And since they're separated because the terms in the Lagrangian are really separated, then you basically, there are no x variables sitting in this equation, and there are z variables sitting in that equation.
So is this also is a way of like doing the first order condition for the multi-variable function for Lagrange multiplier? Since there are two variables, x and z.
Yeah. So if you had two variables in general in the equality constraint and an equality constraint problem, you could do this. But you could two different kinds of variables, if you will, they're kind of separated out. Actually, we'll actually talk about that those kinds of problems a little bit later in the course. Actually, yeah. But you could do that. But there's not much advantage in doing that in general. But in this particular case, separating it out actually is useful because the z's are auxiliary variables. You don't really care about them in establishing the final result. Okay, they're only intermediate variables that help you establish the KKT theorem. Does that make sense?
Yeah, thank you.
Okay. All right, so I think this is a good stopping point. We're about halfway through the notes. So let's take a short break and we'll reconvene in 2 minutes, unless there's any last minute question here. All right, good. Let's reconvene at 11:42 or so. Yeah, 11:42. Oh, looks like I lost the broadcasting. Okay. So any questions before we proceed?
Yes, I just want to double check. So could you go to like a previous page about the proposition KKT, just the definition?
Yeah.
I'm wondering why there's like no constraint about lambda in the search.
Yeah, so actually we saw that before when we just looked at equality constraints, right? That lambda could be positive or negative. Or it doesn't, so it could be, it could also equal 0 in some cases, but lambda could be, and we saw examples of all that. And
Also,
so inequality constraints behave a little bit differently. So maybe, so next, on Thursday, we'll focus on examples. And when we do examples and then maybe draw some pictures corresponding to the examples, you'll get a little more intuition for why the mu j's have to be non-negative for inequality constraints. Okay.
I see. Yeah.
Is that your question?
Oh, by the way, and also for the mu j equal to 0 when that now belongs to the active set, will that collide with the above line? Basically, like is there like will there be any conflict with the the second line, like mu j?
No, because we are allowing for 0, right? In the mu j being non-negative. So some of those mu j's could correspond to the active. All the active ones will be 0, and some of the all the inactive ones will be 0. Some of the active ones could also be 0. Okay.
I see.
Not ruling that out. It's not going to be strictly positive. So it's non-negative. Same with the lambdas, right? Some of the lambdas could be 0, and we saw an example of that in the last lecture last Tuesday, I guess.
Then does it mean we don't actually need the third line? We just need to. I mean, the second line is already.
No, it's important to know that those guys will actually be equal to 0, because then they will not affect your choice of your choice of whether x is regular or not.
I see. Okay, thanks.
Yeah. Another way to write these conditions is to say that the product of the mu j and the gj of x star has to equal 0, because whenever gj of x star is 0, mu j is not 0. It could be non-zero, and the vice versa. The product will always be 0. But we'll talk about that later. So that's why it's called complementary slackness. Okay, and we'll mention that. Maybe we'll talk more about it in the next lecture. Right now, we're going to focus on proving this result. All good questions, so keep them coming. All right, so we can write down these two gradient equations that we had on the previous page. I've just rewritten them here, 1 and 2. And if you actually look at the gradient with respect to z of zj squared, because zj only depends on the jth component, if I look at those gradients with the partials with respect to all the z's, except for the jth component, are going to be 0. And the one corresponding to the jth component will be 2 times zj. So let's write that down. This is 0, 0, and then the jth component will be 2 zj squared, and then 0s everywhere else. Right?
There shouldn't be a square.
2 zj, not square, right? Absolutely. Okay. Jth component. All right. So now let's see what the first equation tells us. The first equation tells us that if this doesn't involve z, right? This equation doesn't involve z. So it's like I have a Lagrangian that only involves x lambda and mu, of course, the x lambda and mu equal to 0. So this is just saying that the gradient of that Lagrangian function that does not involve z is 0. And that was what the Lagrangian function was in the KKT theorem. There was no z in that KKT theorem. Right? Z was an auxiliary variable. Sorry, GA of x. Okay, there we go. So that's the Lagrangian that is only involves x. Okay, so that's what equation 1 tells us, that that's true. Equation 2 tells us, so basically we've from this we already know, we already have one part of the of the KKT theorem. This part we already shown now. Okay, now we have to look at the rest of it. So this is what we need to establish now, and then we'll talk about the second order condition. So we actually get that from 2. Okay, so what does 2 tell us? 2 tells us that if I look at, okay, so think of this guy turn the other way. So as this is actually the transpose, right? It's not, this is a row vector, it's actually between transpose of this. So if I take the transpose, it becomes a column vector with this 2zj in the as the jth component of the column. Okay, and that's being multiplied by mu j, and everywhere else I have a 0 corresponding to the jth term in the summation. So the jth term in summation is a vector, just has 2 mu j zj in the jth component. Okay, and if I add all those vectors together, then I'll get that each component of the vector will correspond to a different product of 2 mu j zj star. All right, so I'll get 2 mu 1 z1 star dot 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 2 mu r zr star is equal to 0. Can we see that? I'm just, turning that row vector around and adding all the components to form that summation, to form this summation. And I get this from that summation. So that has to equal 0, but that means that each of the components has to be 0. J equal to 1 to r. But let's look at what zj star is. Zj star is minus gj x star, which is actually, this minus gj x star is a positive number because gj is strictly less than 0. So this is a positive number. I'm taking square root of that positive number. This is 0. This is positive. Right? Actually, I should say this is not equal to 0. That's enough. So that means that mu j has to be 0 because the product is 0. For j, j not belonging to the active set. So for all j's that are not in the active set, that are inactive, the mu j has to be 0. That's what we established from that second condition. So now let's going back to the statement of KKT, we've established this part. Okay, so we've established this. Now let's get to this part. Everyone with me so far?
Yeah.
Okay, so to establish this part, that mu j's have to be non-negative. Okay, we're actually, in this proof, we're going to assume twice continuously differentiable functions. Okay, but it turns out that you can prove it without that condition. So the textbook actually has a way to prove the same result without requiring twice continuous differentiability. But we're going to assume these are twice continuously differentiable for the second order condition anyway. So in our proof, to keep things simpler, I'm going to assume second order differentiability in order to establish this result, although it's strictly speaking not required. So you can get around it with a longer proof. So we'll go via the second order necessary conditions. So let's first look at the second order necessary conditions. Look at second order necessary conditions for P3. So the problem which we've solved already, right? So we solved in lectures 11 and 12, the equality constraint problem that we've already solved. What does that say? It says that now I have to consider both the x variables and the z variables. Okay, so I'm going to create a dummy variable vector. I'll call that y for the corresponding to the x variables, and a w corresponding to the z variables. Okay, and this product has to be non-negative for all y belonging to Rn and w belonging to R, satisfying gradient of h at x star transpose y equal to 0, y equal to 1 to m. And then I have the other equality constraints corresponding to zj plus the zj squared variables. And the gradient with respect to both x and z, when I take the inner product of that with y and w, that has to also got to be equal to 0. But since the gradient with respect to x and the z's can kind of separate it out, I can first look at the gradient with respect to this is gj of x star transpose y, and then look at the other inner product with the gradient with respect to zj and the w components of w. If I look at that, so I go back and look at the gradient with respect to zj. So that actually has the only non-zero component is in the jth component here, and that's 2 times zj. Okay, and that will get multiplied by the w vector. So think of stacking the w vector below this thing here, w1, and then wj here, and wr transpose. And then you multiply these two vectors, then all that remains in the inner product of those two is just this term, 2zj wj. So that's what I'll have to add to this inner product. That has to equal 0. Okay, so for P3, based on the results, second order necessary condition, this is what I said, I'm going to use twice continuous differentiability to establish mu j is bigger than or equal to 0. For that, I need to use a second order condition for P3. So that's what I'm going to do now. Okay, so I get this. So this is true, that for any y and w satisfying these conditions, I have that this has to be bigger than or equal to 0. I'm going to use this now to establish that mu j is non-negative. How do we do that? Okay. To do that, first we need the Hessian of L, right? With respect to both the X and Z variables. So unless otherwise specified, this will be both X and Z variables. So it really should be XZ, XZ, because, but anyway. But what I'm trying to say is that we have to do it with respect to both variables. But let's look at this function, right? This function. If I look at the Hessian terms in the things in this matrix corresponding to just the X variables, okay, I can put those will sit in the top left corner here. But those will not really involve the Z's, because the Hessian with respect to X and Z's don't really mix with each other, because Z is just an additive component in L. Okay, so what will sit up here in this top left corner is just the Hessian of the Lagrangian involving only X. Okay, so that's an n by n matrix that sits here. Now, if I look at the terms in the Hessian corresponding to the other places here, well, if I look at the second derivative with respect to the Z's, right, so if I look at the first derivative with respect to X, and then I take a derivative with respect to the Z component, okay, that's going to be 0. Because when I take the derivative with respect to X, this will drop out. And then I'm left with nothing involving Z, so the derivative, when I take a partial with respect to Z, it'll go to 0. So all these are going to be 0. Okay. Now let's focus on, so I need to focus on the bottom right matrix, this one. But in this matrix, we already saw that when I take the gradient, I'll just get one non-zero term involving, that's 2 times Zj, right? And when I take a second derivative with respect to that, I'll get just 2. So 2 will multiply mu, so all that will remain in the Hessian with respect to Zj's will be just this diagonal matrix with 2 mu on the diagonal. Is that clear? So now the Hessian that involves both the variables is going to be of this form. All right. So now let me take every j belonging to the active set. For every j belonging to the active set, I'm going to select. I'm going to make different choices for y and w, and use that to establish that the mu j is non-negative. So the choice of y and w, so I just need to make sure that when I choose my y and w, that they satisfy these conditions, Okay, and once they satisfy these conditions, I know that I can apply this, and from this, I'm going to establish that mu j is non-negative. Okay. So for every j in the active set, select y and w with, I can choose that any way I like, but I have to make sure the constraints are satisfied. Right? I'll choose this so that y is equal to 0 and wj equal to 0. Sorry, wk equal to 0, or k not equal to j. And wj is some non-zero number. So now let's see whether yw satisfies the inner product conditions. So if I look at the inner product of hi with y, hi of x star with y, gradient of hi of x star with y. So that inner product has to be 0 because y is 0. If I take the inner product of gk x star with y, that's also 0. And then I made wk is 0 for all k not equal to j. So this whole thing will be 0 for all k not equal to j. So now we are left just with one condition to check. That's a condition that involves gj. So I have gj transpose, what did I do here? Oh, this is great. I forgot to put the gradient sign there, right? Okay, there we go. That's better. So the gradient of gj, but this is again, this part is again 0 because y is 0. And then wj is not 0. But if let's look at zj star, I'm looking at stuff that's active, j that's active. For j that acts as active, what is zj star? There's no gap, right? There's no gap to fill for an active constraint. So gj star is 0. So this whole thing is 0. So basically this YW satisfies the constraints required in the second order condition for the equality constraint problem. Oh boy, what happened here? Okay, there we go. So we've satisfied these conditions, so now we can apply this. So let's go ahead and do that. For this choice of W, we have that this product has to be greater than or equal to 0, but let's see what that implies. Well, this y is 0, so this guy doesn't matter. So that in this product, so this guy disappears. And now let's look at the w, what role w plays. All the w is also 0 except for wj. So for this to be non-negative, we have to have that term corresponding to the only non-zero term will be mu j wj squared, and that has to be non-negative. But wj is not 0, and wj squared is positive. This product has to be non-negative. What does that imply about mu j? Someone?
Greater than or equal to 0.
Yep. So now we just one choice of j belonging to the active set. You can do that for every other j's in a similar manner. So similarly, we can show that mu j is bigger than 0 for all j belonging to the active set. So we have now established this part here. We've established this part. So with all this is done. Now what remains to be shown is the second order condition. Okay. I think I have enough time to do that. But any questions so far? All right. Again, for establishing second order condition, it's just a matter of choosing the y and w vector for P3, or the second order condition for P3 judiciously. So let's do that. Okay. Now, so what we're going to say is, let's assume that y is such that these inner products are all equal to 0. So the inner product of hi with y is 0, and gj with y is 0 for j belonging to the active set. So let's choose our y that way, assuming that we can find such a y. Okay, and then we'll choose our w, given that y. We'll choose our w such that wj is 0 when j is in the active set, and Wj is given by this, actually this product, divided by 2 times Zj star if J is not in the active set. Of course, if J was in the active set, this would be 0. And for those values, we're already setting Wj equal to 0. Okay, so then let's see if our inner product conditions are satisfied. Well, the inner product condition for Hi is already satisfied by assumption. So we don't need to worry about that. So we need to only worry about the inner product condition for the Gj in both the X and the Z variables. So we need to see if this is equal to 0. Okay, first of all, let's focus on things that are not in the active set. For J that's not in the active set, by the way I've constructed Wj, right? If I see that, if I plug that in for Wj, then I'll get this minus itself, so that's equal to 0. So if everything in the active set, this is 0. Sorry, inactive set. Okay, from this condition, we get that this is 0. What about J that's in the active set? But J that's in the active set, we already have up here that this is 0 for J in the active set. So this is 0. And also Wj is 0. So this is 0. So this is also 0 for J in the active set. So both in and out of the active set, this thing is 0. So the conditions, inner product conditions, are satisfied. Okay. Also, we know that Wj is 0. We've said Wj equal to 0 for J in the active set. And we already know from our previous result that mu J is 0 for J that's not in the active set. So if you look at the product of mu J and Wj, that's always going to be 0, no matter whether you're in the active set or not. Mu J times Wj, one of them is going to be 0, right? Whether you're in the active set or not. So for this choice of Wj and y, we have that mu j times Wj must be equal to 0 as well. So given all that, let's see what happens to this product of Yw with the Hessian matrix times Yw. Right? What that says is now I have the top left matrix is going to give me the product of y, this, and y, right? Y transpose, oh, there should be a transpose up here, sorry. Okay. So y transpose this times y, that's one of the terms when I sum this up. And then the other terms will correspond to Wj times the mu j's along these diagonals, right? Wj squared actually times the mu j. But that's 0. So all that will remain from this product is actually what? Someone? What's going to remain in this product?
Y transpose the Hessian y?
Yep, very good. Y transpose the Hessian. Now it's only the Hessian involving the x variables and of the function L that only involves the x variable. Okay, so what we have really shown now is that as long as this condition holds, that only involves the x variables, that this has to be non-negative. And that was the second order necessary condition. Go back here. That's exactly what we said here. Second order necessary condition says that Y transpose the Hessian of L of X lambda mu times y has to be non-negative for all y such that this inner product is 0 and these inner products are 0 for j in the active set only. Okay, so we've basically proved the KKT theorem. All right. So let's actually state that again. So I did that at the end here. So X star be a local minimum for ICP. Assume that X star is regular. And here we only need the gradient of the HIs and the GJs in the active set. If all those gradients are linearly independent, then there exists unique Lagrange multipliers, lambda and mu, such that this is true. And if we further assume, well, actually, we had to assume, in our proof, we had to assume twice differentiability conditions to establish this part. Although there's a way to not do that, which is why the Lagrange multiplier theorem is written this way, that if you further assume twice differentiability conditions, then this holds as well. Okay. Now there's a corresponding sufficiency condition, which sufficiency condition is what you would actually use in looking for local minima or testing if something is a local minimum and so on. And the sufficiency condition, in the sufficiency condition, we first actually have to make sure that the first order necessary conditions are satisfied. So suppose that for X star, there's a lambda and mu that satisfies the first order necessary conditions, these conditions. Well, actually, first order necessary conditions are these. And if, in addition, mu j is strictly positive, not just non-negative, strictly positive for all j in the active set, and this inner product Y transpose Hessian, I made a lot of typos in this, huh? Okay, Oritos should be square there. Hessian Y is positive for all Y not equal to 0. Now we have to consider all Y not equal to 0 such that this is true. Then X star is strict local minimum. And the proof is sufficient condition really, it's in the book. I mean, it's just a few lines. Once you have the necessary conditions, it's essentially just like we did in the unconstrained problem. You kind of go backwards in some sense to get the sufficiency condition. Okay. Now, I mean, a lot of times you may be able to get around checking sufficiency conditions. For example, we saw that even in some of the examples we looked at, that if you know, for example, if when you solve the necessary condition, first order necessary conditions, you end up with an X star that's unique. We saw that with the equality constraint problems, right? Several cases, including the example and the exam that you saw yesterday. And if you can establish separately that there is a global minimum exists for the problem, okay, then there's only one choice for that global minimum, right? Because there was only one choice for the local minimum. So the X star, that unique X star that satisfied the first order necessary conditions must also be the global minimum, because the maximum doesn't exist for that example, coercivity. So that's you could sometimes you can get around the need for looking at the second order sufficient conditions. Okay, but to just be complete, we give the second order sufficient conditions, and a lot of times in the simple examples that you can work out in an exam or in your homework, it's not that hard to check the second order sufficiency condition anyway. So you can rule out things that are not local minima first, and then ask whether that what remains as your candidates for local minimum, which one of those is global. All right, assuming that a global minimum exists. Okay. Any questions? All this will become a little more clear once we start doing examples, just like what happened with the equality constraints. Okay, so we'll spend all of next lecture, maybe even a little bit into next week on examples. And I didn't want to have a homework due a week from now because you just had an exam. And so we'll wait for 2 weeks. So 2 weeks from today is when homework 5 will be due. And you'll probably, homework 4 will be due. And you'll probably only have a total of 5 homework assignments before the second exam. And I'll make the second exam comprehensive. In other words, it'll include all the material because there's not going to be a final exam for you guys. So. All right. Okay, so I'll see you guys on Thursday.